India, with its rich biodiversity and unique ecosystems, is home to a diverse range of flora and fauna. However, the country's rapid urbanization, industrialization, deforestation, and habitat destruction have led to decline and threat to many species. The classification of species into extinct, rare, endangered, and threatened categories is crucial for understanding conservation priorities and implementing effective protection measures. The conservation status of species is determined by international organizations such as the International Union for Conservation of Nature (IUCN), which categorizes species based on their risk of extinction. Extinct flora and fauna of India. Extinction refers to the complete disappearance of a species from the planet. In India, a number of plant and animal species have gone extinct, mainly due to habitat loss, hunting, and overexploitation. Flora. Rheum australe Himalayan rhubarb, this plant species, native to the high altitudes of the Himalayas, has been declared extinct due to overharvesting for medicinal use and habitat destruction. Cinnametra ramiflora, Indian rosewood, once found in tropical forests, this species is believed to be extinct, primarily due to logging and habitat conversion for agriculture. Fauna. Indian cheetah Acinonyx jubatus venaticus, the Indian cheetah, once found across the Indian subcontinent, was declared extinct in India in the 1950s due to hunting, habitat destruction, and loss of prey species. Javan tiger Panthera tigris sondiga, the Javan tiger, once native to the island of Java, is considered extinct due to habitat destruction and hunting. The pink-headed duck Rhodonus acariophilus, this species, which was native to wetlands in India, was last reported in the early 20th century and is now considered extinct due to habitat loss and hunting. Rare flora and fauna of India. Rare species are those that are not necessarily endangered but are found in very limited populations or specific areas. These species require conservation attention to prevent them from becoming endangered or extinct. Flora. Edelweiss leontopidium alpinum, this beautiful alpine flower, found in the higher reaches of the Himalayas, is rare and highly prized for its medicinal properties. Sundari tree Caratiera fomes, a rare tree species found in the mangrove forests of the Sundarbans. This tree is important for coastal ecosystems and is under threat due to the loss of mangrove habitats. Fauna. Himalayan monal Liphophorus impohanus, the state bird of Himachal Pradesh and Uttarakhand. This striking bird is rare and found in the higher Himalayas. The species is under threat due to habitat destruction and hunting. Nilgiri tar, Nilgiri trigus hylocrius, a rare mountain goat species found in the Nilgiri hills of southern India. The Nilgiri tar faces threats from habitat loss and human encroachment. Endangered flora and fauna of India. Endangered species are those that are at a high risk of extinction in the near future, primarily due to human-induced factors such as habitat destruction, poaching, and climate change. Flora. Sausage tree Kichlia africana, found in parts of India's northeastern region. This tree is classified as endangered due to habitat destruction and overexploitation for its fruit, which has medicinal properties. Indian ghost tree Erythrina variegata, an endangered species found in coastal regions of India. It is threatened by habitat loss due to coastal development. Fauna. Bengal tiger Panthera tigris tigris. The Bengal tiger is one of the most iconic endangered species of India. It faces threats from poaching, habitat destruction, and human-wildlife conflict. Conservation efforts have been made through Project Tiger, but the species remains endangered. Indian Elephas maximus indicus. The Indian elephant is endangered due to habitat fragmentation, poaching for tusks, and human-elephant conflict. The population of these elephants has significantly reduced, and they are now primarily confined to protected areas and reserves. One-horned rhinoceros Rhinoceros unicornis, once widespread in the Indian subcontinent. This species is now confined to protected areas like Kaziranga National Park in Assam. Poaching for its horn and habitat loss have led to a significant reduction in its population. Threatened flora and fauna of India. Threatened species are those that are likely to become endangered in the near future if the factors affecting them are not addressed. These species may face a range of threats, including habitat loss, pollution, poaching, and climate change. Flora. Sal tree Chiria robusta. The sal tree, which is a dominant species in India's tropical forests, is threatened by logging, forest fires, and illegal harvesting. Indian vale eagle marmelos. This fruit tree, important for medicinal purposes, faces threats from deforestation and overharvesting. Fauna. Asiatic lion Panthera leo persica. The Asiatic lion, once widespread across the Indian subcontinent, is now confined to the Gir forest in Gujarat. Its population is threatened by poaching, loss of prey, and habitat fragmentation. Great Indian bustard Ardiobus nigriceps. This critically endangered bird species is found in parts of Rajasthan, Gujarat, and Maharashtra. It is threatened by hunting, habitat destruction, and collisions with power lines. Indian crocodile Crocodylus palustris, once widespread across India's rivers and lakes. The Indian crocodile is now considered vulnerable due to habitat loss, poaching, and water pollution. Conservation efforts and the role of protected areas. India has made significant efforts in the conservation of its threatened and endangered species through various initiatives such as Project Tiger, launched in 1973. This project aims to conserve the Bengal tiger and its habitats through the establishment of protected reserves and national parks. Project Elephant, launched in 1992. This project focuses on the conservation of elephants and their habitats across India. Wildlife Protection Act 1972. This act provides a legal framework for the protection of wildlife and their habitats in India, including the establishment of national parks and wildlife sanctuaries. Biosphere reserves and protected areas. These areas, including national parks, wildlife sanctuaries, and wetlands, provide safe havens for endangered species, and efforts are underway to expand and strengthen these reserves. Previous year questions with answers. Q. Which of the following is a critically endangered species in India? A. The great Indian bustard Ardiobus nigriceps is critically endangered due to habitat loss and hunting. UGC NET 2020. Q. What is the main threat to the population of the Bengal tiger in India? A. The primary threat to the Bengal tiger's population is habitat destruction due to deforestation and poaching. UGC NET 2019. Q. Which extinct species was once found in the Indian subcontinent? A. The Indian cheetah Acinonyx jubatus venaticus was declared extinct in India in the 1950s due to hunting and habitat destruction. A. The Indian cheetah Acinonyx jubatus venaticus was declared extinct in India in the 1950s due to hunting and habitat destruction. UGC NET 2021. Q. What is the conservation status of the Asiatic lion Panthera leo persica? A. The Asiatic lion is classified as endangered due to poaching and habitat fragmentation. UGC NET 2022. Q. Which of the following species is considered rare in India? A. The Nilgiri tar Nilgiri trigus hylocrius is a rare species found in the Nilgiri hills of southern India. UGC NET 2021. Conclusion. India's flora and fauna face significant challenges, with many species falling under categories such as extinct, rare, endangered, and threatened. These categories highlight the need for focused conservation efforts to prevent further loss of biodiversity. Despite significant challenges, India's efforts in wildlife protection through projects, legal frameworks, and protected areas have had a positive impact. However, continued awareness, stringent laws, and conservation actions are necessary to protect and preserve India's precious biodiversity for future generations. You said. Concept of industrial ecology. ChatGPT said. Concept of industrial ecology. UGC NET JRF Environmental Science. High-level lecture with maximum word limit. Paragraph format based on previous year questions in key areas. Industrial ecology, i.e., is an interdisciplinary field that applies ecological concepts and principles to the design and operation of industrial systems. It aims to understand and optimize the interactions between industrial processes and the environment. The core idea behind industrial ecology is to create sustainable industrial practices that minimize negative environmental impacts, conserve natural resources, and close the loop of material and energy flows within industries. In other words, it seeks to integrate industrial systems into the natural ecosystem in such a way that waste, energy consumption, and material use are reduced, and ecological sustainability is promoted. Fundamental principles of industrial ecology. Material flow analysis (MFA). Industrial ecology begins by analyzing the flow of materials and energy in industrial systems. This involves tracing the inputs, raw materials, energy, and outputs, products, emissions, waste to identify inefficiencies and areas for improvement. The goal is to reduce the use of virgin materials and minimize waste by reusing or recycling byproducts. The concept of closing the loop is central to IE, where waste from one process becomes a raw material for another. Life cycle assessment (LCA). Life cycle assessment is a key tool. Industrial ecology (IE) is an interdisciplinary field that applies ecological concepts and principles to the design and operation of industrial systems. It aims to understand and optimize the interactions between industrial processes and the environment. The core idea behind industrial ecology is to create sustainable industrial practices that minimize negative environmental impacts, conserve natural resources, and close the loop of material and energy flows within industries. In other words, it seeks to integrate industrial systems into the natural ecosystem in such a way that waste, energy consumption, and material use are reduced, and ecological sustainability is promoted. Fundamental principles of industrial ecology. Material flow analysis (MFA). Industrial ecology begins by analyzing the flow of materials and energy in industrial systems. This involves tracing the inputs, raw materials, energy, and outputs, products, emissions, waste to identify inefficiencies and areas for improvement. The goal is to reduce the use of virgin materials and minimize waste by reusing or recycling byproducts. The concept of closing the loop is central to IE, where waste from one process becomes a raw material for another. Life cycle assessment (LCA). Life cycle assessment is a key tool in industrial ecology. It evaluates the environmental impact of a product or process from cradle to grave, starting from the extraction of raw materials cradle to the end of the product's life grave. By considering every phase of the product life cycle, LCA helps in identifying opportunities for reducing environmental impacts, whether it's through energy-efficient manufacturing, reducing emissions, or designing products for easier recycling. Eco-industrial networks. Eco-industrial networks involve collaboration among industries to create synergistic relationships whereby products or waste of one industry are used as inputs for another. This is analogous to the concept of an ecosystem, where waste products of one organism become resources for another. Such symbiotic relationships can significantly reduce resource consumption, waste production, and pollution while enhancing the overall efficiency of the system. Industrial symbiosis. Industrial symbiosis refers to the collaboration between different industries or companies to share resources, such as energy, water, and materials. For instance, one company's waste heat may be used by another company as an energy source, or a chemical waste stream may be used in the production of another product. Industrial symbiosis reduces waste, lowers costs, and enhances resource efficiency. This practice is often seen in eco-industrial parks or clusters, where various industries operate in close proximity and exchange materials and energy. Sustainable design and green manufacturing. Industrial ecology promotes the concept of sustainable design, which involves creating products and processes that are not only economically viable but also environmentally friendly. Green manufacturing focuses on reducing energy consumption, minimizing the use of hazardous materials, and enhancing the recyclability of products. These approaches aim to reduce the ecological footprint of industrial activities while ensuring that products meet both consumer needs and environmental standards. Circular economy. A core tenet of industrial ecology is the idea of a circular economy, where products and materials are continuously reused, refurbished, or recycled, rather than disposed of after use. This contrasts with the traditional linear economy, which follows a take, make, dispose pattern. In a circular economy, the goal is to Industrial ecology (IE) is an interdisciplinary field that applies ecological concepts and principles to the design and operation of industrial systems. It aims to understand and optimize the interactions between industrial processes and the environment. The core idea behind industrial ecology is to create sustainable industrial practices that minimize negative environmental impacts, conserve natural resources, and close the loop of material and energy flows within industries. In other words, it seeks to integrate industrial systems into the natural ecosystem in such a way that waste, energy consumption, and material use are reduced, and ecological sustainability is promoted. Fundamental principles of industrial ecology. Material flow analysis (MFA). Industrial ecology begins by analyzing the flow of materials and energy in industrial systems. This involves tracing the inputs, raw materials, energy, and outputs, products, emissions, waste to identify inefficiencies and areas for improvement. The goal is to reduce the use of virgin materials and minimize waste by reusing or recycling byproducts. The concept of closing the loop is central to IE, where waste from one process becomes a raw material for another. Life cycle assessment (LCA). Life cycle assessment is a key tool in industrial ecology. It evaluates the environmental impact of a product or process from cradle to grave, starting from the extraction of raw materials cradle to the end of the product's life grave. By considering every phase of the product life cycle, LCA helps in identifying opportunities for reducing environmental impacts, whether it's through energy-efficient manufacturing, reducing emissions, or designing products for easier recycling. Eco-industrial networks. Eco-industrial networks involve collaboration among industries to create synergistic relationships whereby products or waste of one industry are used as inputs for another. This is analogous to the concept of an ecosystem, where waste products of one organism become resources for another. Such symbiotic relationships can significantly reduce resource consumption, waste production, and pollution while enhancing the overall efficiency of the system. Industrial symbiosis. Industrial symbiosis refers to the collaboration between different industries or companies to share resources, such as energy, water, and materials. For instance, one company's waste heat may be used by another company as an energy source, or a chemical waste stream may be used in the production of another product. Industrial symbiosis reduces waste, lowers costs, and enhances resource efficiency. This practice is often seen in eco-industrial parks or clusters, where various industries operate in close proximity and exchange materials and energy. Sustainable design and green manufacturing. Industrial ecology promotes the concept of sustainable design, which involves creating products and processes that are not only economically viable but also environmentally friendly. Green manufacturing focuses on reducing energy consumption, minimizing the use of hazardous materials, and enhancing the recyclability of products. These approaches aim to reduce the ecological footprint of industrial activities while ensuring that products meet both consumer needs and environmental standards. Circular economy. A core tenet of industrial ecology is the idea of a circular economy, where products and materials are continuously reused, refurbished, or recycled, rather than disposed of after use. This contrasts with the traditional linear economy, which follows a take, make, dispose pattern. In a circular economy, the goal is to keep materials in use for as long as possible, thus reducing the demand for new resources and minimizing environmental impacts. Key benefits of industrial ecology. Resource efficiency. By focusing on optimizing the use of materials and energy, industrial ecology helps in reducing resource consumption. This leads to lower production costs, as industries can rely more on recycling and reusing materials, rather than constantly sourcing new raw materials. Waste reduction. Industrial ecology promotes the idea that waste is a resource waiting to be reused. Through innovative processes such as recycling, waste to energy conversion, and waste exchange, industries can reduce their environmental footprint by diverting waste from landfills and minimizing pollution. Economic benefits. The principles of industrial ecology can lead to significant cost savings through resource efficiency and waste reduction. Businesses that adopt IE principles can reduce operational costs, improve profitability, and even create new revenue streams by selling byproducts to other industries. Environmental protection. Industrial ecology contributes to reducing the overall environmental impact of industrial activities by minimizing emissions, reducing toxic waste generation, and promoting sustainable use of natural resources. By applying ecological principles to industrial design, it is possible to create processes that harmonize with the natural environment. Enhanced innovation. Industrial ecology encourages companies to think outside the traditional model of industrial processes. This fosters innovation in product design, manufacturing processes, and resource management, leading to the development of new technologies and business models that are both environmentally and economically sustainable. Challenges and criticisms. Despite the promising benefits, the implementation of industrial ecology faces several challenges. Complexity of systems. Industrial systems are often highly complex, with interconnected processes, supply chains, and diverse stakeholders. This makes it difficult to implement industrial ecology principles effectively across the entire system. High initial costs. Transitioning to a more sustainable industrial model often requires significant investment in new technologies, infrastructure, and training. The high initial costs can be a barrier for smaller industries or businesses without the capital to invest in green technologies. Lack of regulations and incentives. In some regions, there are insufficient regulations or financial incentives to encourage industries to adopt industrial ecology practices. Stronger government policies, tax incentives, and regulatory frameworks are essential to incentivize industries to adopt more sustainable practices. Market challenges. The shift to circular and sustainable economies often faces resistance from markets that are accustomed to the linear model. There may be challenges in scaling up recycling programs or establishing a demand for recycled materials, as the market for such materials is often limited. Previous year questions with answers. Q. Which of the following best describes the concept of industrial ecology? A. Industrial ecology focuses on optimizing material and energy flows in industrial systems to minimize waste, reduce resource consumption, and promote environmental sustainability. UGC/NET 2020. Q. What is the primary goal of life cycle assessment (LCA) in industrial ecology? A. The primary goal of LCA is to evaluate the environmental impact of a product or process from its creation to its disposal, identifying opportunities for reducing negative impacts at each stage of the product life cycle. UGC/NET 2021. Q. What is the concept of industrial symbiosis in industrial ecology? A. Industrial symbiosis refers to the collaboration between industries to share resources such as energy, materials, and byproducts to reduce waste, lower costs, and enhance resource efficiency. UGC/NET 2019. Q. How does industrial ecology contribute to sustainable development? A. Industrial ecology contributes to sustainable development by promoting resource efficiency, reducing waste, and minimizing the environmental impact of industrial activities, thus supporting long-term ecological balance. UGC/NET 2020. Q. Which of the following is a key characteristic of a circular economy, a concept related to industrial ecology? A. A key characteristic of a circular economy is the continuous reuse, recycling, and refurbishment of products and materials, thereby reducing the demand for new resources and minimizing waste. UGC/NET 2022. Conclusion. Industrial ecology offers a promising approach to achieving sustainable industrial development by integrating ecological principles into industrial practices. By promoting resource efficiency, waste reduction, and life cycle thinking, industrial ecology can help industries reduce their environmental impact and move towards a more sustainable future. The application of concepts like industrial symbiosis, life cycle assessment, and circular economy principles can create new business opportunities, reduce costs, and contribute to a healthier environment. However, to fully realize the benefits of industrial ecology, a coordinated effort is required from industries, governments, and consumers to overcome challenges such as high implementation costs and regulatory barriers. You said. Toxicology and microbiology. ChatGPT said. Toxicology and microbiology. Concepts, applications, and interactions in environmental science. UGC NET JRF Environmental Science. High-level lecture with maximum word limit. Paragraph format based on previous year questions and key areas. Toxicology and microbiology are two integral fields within environmental science, particularly when studying the impact of pollutants, pathogens, and contaminants on human health, ecosystems, and biodiversity. Both fields intersect, as many microorganisms can produce toxic compounds, and environmental pollutants can affect microbial populations and ecosystems. Understanding toxicology and microbiology is crucial for assessing environmental risks, understanding disease transmission, and developing effective mitigation strategies. Toxicology, definition, principles, and applications. Toxicology is a scientific study of the adverse effects of chemicals, physical agents, and biological substances on living organisms. It involves understanding the mechanisms by which these substances cause harm and determining safe exposure levels. The field can be divided into several subdisciplines, such as environmental toxicology, clinical toxicology, and forensic toxicology, each focusing on different aspects of toxic substances and their effects on health and ecosystems. Key principles of toxicology. Dose-response relationship. The dose-response relationship is a fundamental concept in toxicology, suggesting that the severity of a toxic effect is dependent on the dose of a substance. As the dose increases, so does the probability of an adverse effect. Toxicologists use this relationship to establish safe exposure levels and thresholds for chemicals. Toxicokinetics and toxicodynamics. Toxicokinetics refers to the absorption, distribution, metabolism, and excretion ADME of toxic substances in the body. Toxicodynamics, on the other hand, focuses on the mechanisms by which a toxic substance exerts its harmful effects on cellular and molecular targets. Both are essential for understanding how toxins interact with organisms at different levels. Types of toxicity. Acute toxicity occurs after a single or short-term exposure to a high concentration of a substance, leading to immediate harmful effects. Chronic toxicity develops after prolonged exposure to low levels of a substance, often resulting in long-term health effects like cancer, organ damage, or neurological impairments. Developmental and reproductive toxicity involves effects on the development of embryos or offspring, or impacts reproductive health, including infertility and birth defects. Ecotoxicology. Ecotoxicology is a subdiscipline of toxicology that studies the impact of toxic chemicals on ecosystems, including plants, animals, and microorganisms. It examines the bioaccumulation and biomagnification of pollutants in food chains, emphasizing how these chemicals affect biodiversity and ecosystem health. Applications of toxicology in environmental science. Toxicology plays a vital role in risk assessment, pollution control, and environmental management. It helps identify harmful substances in air, water, soil, and food, and provides guidelines for regulating their use. It is also central to the study of hazardous waste management and the development of strategies for preventing chemical spills, contamination, and the spread of toxins in the environment. Microbiology, definition, principles, and applications. Microbiology is the study of microorganisms, which include bacteria, viruses, fungi, protozoa, and algae. Microorganisms play both beneficial and harmful roles in the environment. While some are essential for nutrient cycling, others are pathogenic and can cause diseases in humans, animals, and plants. Key principles of microbiology. Microbial ecology. Microbial ecology studies the interactions between microorganisms and their environment. Microbes are crucial for maintaining ecological balance, performing essential processes such as nitrogen fixation, organic matter decomposition, and carbon cycling. The role of microbes in ecosystem functions makes them indispensable in maintaining soil health, water quality, and atmospheric balance. Pathogenic microorganisms. Many microorganisms can act as pathogens, causing diseases in humans, animals, and plants. The study of pathogenic microorganisms helps in understanding the mechanisms of infection, disease transmission, and the development of antimicrobial resistance. Microbiologists study bacteria, viruses, and fungi that can contaminate food, water, and the air, leading to epidemics or chronic diseases. Antimicrobial resistance is a growing global concern, as the overuse and misuse of antibiotics and other antimicrobial agents in both healthcare and agriculture have led to the development of resistant strains of bacteria and other pathogens. This resistance threatens the effectiveness of treatment options, making infections harder to treat and leading to higher mortality rates. Microbiology plays a key role in studying the development and spread of and finding alternative solutions for treating resistant infections. Microbial identification and diagnosis. Microbiologists use a variety of methods to identify microorganisms and diagnose infections. Techniques like culturing, polymerase chain reaction (PCR), and sequencing are used to detect specific pathogens. Microbiological diagnostic tools are essential in public health for monitoring disease outbreaks, ensuring food safety, and identifying environmental contamination. Applications of microbiology in environmental science. Bioremediation. Bioremediation is the use of microorganisms to clean up environmental pollutants, such as oil spills, heavy metals, and pesticides. Certain bacteria and fungi can degrade harmful chemicals, converting them into less toxic substances or using them as energy sources. This biotechnological approach is a sustainable alternative to chemical-based remediation methods. Water quality monitoring. Microbiology plays a crucial role in water quality testing. Microbial contamination of water sources can lead to the spread of waterborne diseases such as cholera and dysentery. Microbiological tests like coliform testing help identify harmful pathogens in drinking water, ensuring public health safety. Soil fertility and agricultural microbiology. Microorganisms contribute to soil fertility by decomposing organic matter and fixing nitrogen, which is essential for plant growth. Agricultural microbiology focuses on studying soil microbes and their role in enhancing crop yield, preventing plant diseases, and promoting sustainable farming practices. Interactions between toxicology and microbiology. The fields of toxicology and microbiology often intersect, particularly in environmental science. Many toxic substances, such as heavy metals, pesticides, and industrial chemicals, have direct impacts on microbial populations. Toxicants can alter the diversity and function of microbial communities, disrupting key ecological processes like nutrient cycling and organic matter decomposition. Conversely, some microorganisms can produce toxic substances, including biotoxins, that can pose a significant threat to human health and the environment. The relationship between toxicology and microbiology is particularly relevant in the context of bioremediation, where microorganisms are used to degrade or neutralize toxic pollutants. Understanding the toxic effects of chemicals on microbial metabolism is essential for optimizing bioremediation strategies and ensuring the health of microbial ecosystems. Previous year questions with answers. Q. Which of the following is the primary focus of ecotoxicology? I. Ecotoxicology focuses on the study of the adverse effects of chemical pollutants on ecosystems, including impacts on plants, animal, and microorganisms. UGC-NET 2019. Q. What is the main function of the dose-response relationship in toxicology? The dose-response relationship helps determine the severity of toxic effects based on the concentration or dose of a substance, which is crucial for setting safety standards and exposure limits. UGC-NET 2020. Q. What is bioremediation? Bioremediation is the use of microorganisms to break down environmental pollutants, such as oil spills, heavy metals, and pesticides, into less harmful substances. UGC-NET 2021. Q. What role do bacteria play in the nitrogen cycle? Bacteria play a vital role in nitrogen fixation, converting atmospheric nitrogen into forms that can be used by plants, thus maintaining soil fertility. UGC-NET 2020. Q. Which of the following is a common example of a pathogenic microorganism in water? Escherichia coli, E. coli, is a common pathogenic bacterium found in contaminated water that can cause gastrointestinal infections. UGC-NET 2019. Conclusion. Toxicology and microbiology are foundational fields in environmental science that contribute to our understanding of environmental risks and the functioning of ecosystems. Toxicology provides the tools to assess and manage the harmful effects of chemicals and pollutants on living organisms, while microbiology offers insight into the role of microorganisms in ecological processes and public health. Together, they help us develop sustainable practices for environmental protection, pollution control, and disease management. By studying the intersection of these fields, we can better understand how contaminants affect ecosystems and human health, and develop effective strategies for mitigating environmental harm. You said. Absorption, distribution, and excretion of toxic agents. ChatGPT said. Absorption, distribution, and excretion of toxic agents. Concepts and mechanisms in environmental toxicology. UGC-NET JRF Environmental Science. High-level lecture with maximum word limit. Paragraph format based on previous year questions in key areas. The absorption, distribution, and excretion of toxic agents are fundamental processes in toxicology that describe how harmful substances enter the body, spread through tissues and organs, and are eventually eliminated. These processes determine the extent of toxicity and the potential risks posed by chemicals, pollutants, and other toxic agents. Understanding the 8 mechanisms is essential for assessing the environmental and health impacts of exposure to toxic substances and for formulating safety guidelines. Absorption of toxic agents. Absorption refers to the process by which toxic agents enter the body from the external environment. The route of absorption largely depends on the physical state of the toxic agent: solid, liquid, gas, its chemical properties, and the exposure route: inhalation, ingestion, skin contact. Key factors influencing absorption: route of exposure. Inhalation: gaseous and particulate toxins enter the body through the respiratory system. The lungs have a large surface area for absorption, making inhalation a common route for toxicants like pollutants, industrial chemicals, and biotoxins. Ingestion: toxic agents may be absorbed via the gastrointestinal tract after ingestion of contaminated food or water. The stomach and intestines absorb chemicals into the bloodstream for systemic distribution. Dermal exposure: some toxicants, particularly lipophilic fat-soluble compounds, can pass through the skin and enter systemic circulation. Dermal exposure is common in occupational settings or through pesticide use. Physical and chemical properties of the toxin. Lipophilicity, fat solubility. Lipophilic toxins tend to pass through cell membranes more easily than hydrophilic, water-soluble compounds, affecting their absorption rate. Molecular size: small molecules are typically absorbed more readily than large molecules, as they can more easily diffuse across cellular membranes. Ionization: the degree of ionization of a toxic substance affects its absorption. Non-ionized molecules are more readily absorbed, as ionized compounds often have poor membrane permeability. Transport mechanisms: the absorption of toxins may occur through passive diffusion, facilitated diffusion, or active transport mechanisms. In passive diffusion, toxicants move from areas of higher concentration to lower concentration across biological membranes. Active transport requires energy to move toxins against concentration gradients, a process that can be influenced by specific transport proteins. Distribution of toxic agents. Once absorbed, toxic agents are distributed throughout the body via the circulatory system. The distribution pattern depends on various factors, such as blood flow to tissues, the toxicant's ability to cross cellular membranes, and the affinity of the agent for certain tissues or organs. Key factors influencing distribution. Blood flow: organs with higher blood flow, such as the liver, kidneys, heart, and brain, are typically exposed to higher concentrations of toxins. This is why certain organs may be more susceptible to damage from toxic agents. Affinity for tissues: some toxic agents have a higher affinity for specific tissues. For example, lipophilic fat-soluble toxins, such as organochlorine pesticides, tend to accumulate in fatty tissues, including the brain, liver, and adipose tissue. Heavy metals like mercury and lead have an affinity for bone tissue, where they can accumulate over time. Plasma protein binding: many toxic substances bind to plasma proteins, such as albumin, in the bloodstream. This binding reduces the free concentration of the toxin available to interact with target tissues. However, when these substances are released from the proteins, they can exert their toxic effects. Blood-brain barrier and placental barrier: the blood-brain barrier (BBB) is a selective barrier that protects the brain from harmful substances. However, some toxins, such as lead or mercury, can cross the BBB and affect the nervous system. Similarly, the placental barrier can restrict the passage of certain toxins, but many substances, such as alcohol and heavy metals, can still cross, potentially harming the fetus. Half-life and bioaccumulation. Half-life and bioaccumulation: the half-life of a toxin, which is the time it takes for half of a substance to be eliminated from the body, influences its distribution. Some toxins, like persistent organic pollutants, accumulate over time in the body's tissues through bioaccumulation and biomagnification, leading to long-term exposure. Excretion of toxic agents. Excretion is the process by which the body eliminates toxic substances. Excretion primarily occurs through the urinary, biliary, feces, and pulmonary routes. The efficiency of excretion influences how long a toxic agent remains in the body and how its toxic effects manifest. Key excretion routes. Renal excretion, urinary system. The kidneys filter the blood to remove waste products, including many toxic agents. Renal excretion, urinary system. The kidneys filter the blood to remove waste products, including many toxic agents. Water-soluble toxins, particularly those that are ionized or small in size, are excreted in the urine. The process involves glomerular filtration, tubular secretion, and reabsorption. The kidneys also regulate the pH of urine, which can affect the excretion of certain toxins. Hepatic excretion, fecal system. Some toxic agents, especially lipophilic substances, are metabolized in the liver and excreted in bile. These compounds are then transported to the intestines and eliminated in feces. The liver plays a central role in biotransformation metabolism by converting fat-soluble toxins into water-soluble metabolites, which can be more easily excreted. Pulmonary excretion, respiratory system. Volatile toxicants, such as alcohol and some industrial chemicals, are exhaled through the lungs. This route is significant for gases or substances with low molecular weight that can easily diffuse from the bloodstream into the alveoli of the lungs. Sweat and salivary excretion. Although less significant, some toxins can be excreted through sweat and saliva. This is often observed in cases of heavy metal exposure, such as arsenic or cadmium. Excretion and bioaccumulation. In cases of bioaccumulation, toxic agents may persist in the body because they are not efficiently excreted. This is particularly true for persistent organic pollutants, POPs, which tend to accumulate in fatty tissues and can remain in the body for long periods, causing chronic toxic effects. Factors influencing excretion. Metabolic rate. The rate of metabolism of toxic agents can affect how quickly they are excreted. Individuals with a faster metabolism may eliminate toxins more rapidly, reducing their overall exposure. Agent health status. The efficiency of excretion can vary with age and health. For instance, children and the elderly often have reduced kidney and liver function, leading to slower clearance of toxic agents. Additionally, individuals with liver or kidney diseases may experience impaired excretion, leading to a higher risk of toxicity. Environmental conditions. Environmental factors, such as temperature, diet, and exposure to other chemicals, can also influence how effectively toxins are excreted from the body. For example, high temperatures can increase sweating, promoting the excretion of certain toxins. Previous year questions with answers. Q. What are the primary routes of absorption of toxic substances into the body? The primary routes of absorption include inhalation, ingestion, and dermal exposure. UGC NET 2020. Q. How does the blood-brain barrier influence the distribution of toxic agents? The blood-brain barrier selectively prevents the entry of many toxic agents into the brain, but some substances, such as lead and mercury, can cross the barrier and cause neurological damage. UGC NET 2021. Q. Which organ is primarily responsible for the excretion of water-soluble toxins? Q. What are the primary routes of absorption of toxic substances into the body? The primary routes of absorption include inhalation, ingestion, and dermal exposure. UGC NET 2020. Q. How does the blood-brain barrier influence the distribution of toxic agents? The blood-brain barrier selectively prevents the entry of many toxic agents into the brain, but some substances, such as lead and mercury, can cross the barrier and cause neurological damage. UGC NET 2021. Q. Which organ is primarily responsible for the excretion of water-soluble toxins? The kidneys are primarily responsible for the excretion of water-soluble toxins through urine. UGC NET 2020. Q. What is biotransformation, and which organ is involved in this process for the excretion of toxic agents? Biotransformation is the process by which the liver metabolizes lipophilic toxins into water-soluble metabolites for easier excretion. UGC NET 2021. Q. Why are persistent organic pollutants, POPs, a concern in terms of bioaccumulation? POPs are lipophilic and tend to accumulate in fatty tissues, where they persist over time, leading to chronic exposure and long-term health risks. UGC NET 2020. Conclusion. The absorption, distribution, and excretion of toxic agents are essential processes for understanding how pollutants and chemicals affect the body and the environment. These processes determine how long a toxic substance remains in the system, how it reaches various organs, and how it is eliminated from the body. Environmental toxicologists focus on understanding these mechanisms to predict and mitigate the harmful effects of exposure to toxic agents. Through careful monitoring of these processes, public health guidelines and environmental protection strategies can be developed to reduce the risks associated with chemical pollutants. You said. Acute and chronic toxicity. ChatGPT said. Acute and chronic toxicity. Concepts, mechanisms, and impacts in environmental toxicology. UGC NET JRF Environmental Science. High-level lecture with maximum word limit. Paragraph format based on previous year questions and key areas. Toxicity refers to the degree to which a substance can damage an organism, and understanding the differences between acute and chronic toxicity is critical in assessing the environmental and health risks associated with exposure to toxic agents. These two types of toxicity are differentiated by the duration, severity, and nature of the exposure to the toxic agent. Both acute and chronic toxicity can have serious implications for human health, wildlife, and ecosystems, making them key areas of study in environmental science and toxicology. Acute toxicity. Acute toxicity is the harmful effect of a toxic substance that results from a single exposure or multiple exposures over a short period of time, typically within 24 hours. The effects of acute toxicity are usually rapid and severe, and they can result in immediate harm to the organism, including death in extreme cases. Acute toxicity is typically used to determine the lethal dose LD50, which is the amount of the substance that causes death in 50% of a test population. Key characteristics of acute toxicity. Short exposure duration. Acute toxicity occurs after a single or short-term exposure, typically within 24 hours. The substance can enter the body via ingestion, inhalation, or dermal absorption. Rapid onset of symptoms. The symptoms of acute toxicity appear quickly after exposure, ranging from mild to severe. These may include nausea, vomiting, dizziness, convulsions, respiratory failure, and in extreme cases, death. Dose-dependent effects. The severity of the toxicity is often related to the dose. A higher dose of the toxic substance can lead to more severe outcomes, including death. Acute toxicity tests. The primary measure of acute toxicity is the LD50 or LC50, lethal concentration for 50% of the population, which provides a benchmark for comparing the toxicity of different substances. Animal testing, such as the acute oral toxicity test, is often used to determine these values. Acute toxicity example. The ingestion of a toxic substance like cyanide or the inhalation of carbon monoxide may lead to rapid onset symptoms and death. Acute toxicity testing is commonly used for pesticides, industrial chemicals, and environmental pollutants to determine immediate risks. Previous year question. UGC NET 2020. Q. What is the primary measure used to assess acute toxicity in laboratory animals? The primary measure is the LD50, which refers to the lethal dose of a substance that causes death in 50% of the test population. UGC NET 2020. Chronic toxicity. Chronic toxicity refers to the harmful effects of a substance that result from long-term exposure over a prolonged period, often lasting months or years. Unlike acute toxicity, the effects of chronic toxicity may not be immediately apparent but can accumulate over time, leading to long-term health problems such as cancer, liver damage, reproductive issues, and neurological impairments. Key characteristics of chronic toxicity. Long exposure duration. Chronic toxicity results from continuous or repeated exposure to a toxic substance over an extended period, often months to years, which may occur at lower concentrations compared to acute toxicity. Delayed onset of symptoms. Symptoms of chronic toxicity may not appear immediately, and the effects accumulate over time. Common signs include liver damage, kidney disease, and neurological impairments. In many cases, the toxic effects only become evident after years of exposure. Cumulative effects. Chronic exposure to lower levels of toxic substances can lead to cumulative damage to organs and tissues, which may not be reversible. For instance, exposure to low levels of lead over many years can cause irreversible neurological damage, particularly in children. Carcinogenicity and mutagenicity. Chronic toxicity is often associated with substances that are carcinogenic, cancer-causing, or mutagenic, causing genetic mutations. Long-term exposure to carcinogens like asbestos or benzene may lead to the development of cancer decades after exposure. Chronic toxicity example. Substances like asbestos, benzene, and some pesticides exhibit chronic toxicity. Prolonged exposure to these chemicals can lead to long-term health effects, such as lung cancer, leukemia, and reproductive disorders. Previous year question. UGC NET 2021. Q. Which of the following is an example of chronic toxicity due to long-term exposure? Prolonged exposure to asbestos can cause lung cancer, a form of chronic toxicity. UGC NET 2021. Differences between acute and chronic toxicity. While both acute and chronic toxicity can cause severe damage, they differ in several ways, including the duration of exposure, the time course of symptoms, and the severity of the health effects. Key differences. Exposure duration. Acute toxicity results from short-term exposure, usually within 24 hours. Chronic toxicity results from long-term exposure, which may last for months or years. Onset of symptoms. Acute toxicity. Symptoms appear rapidly after exposure, often within minutes or hours. Chronic toxicity. Symptoms develop gradually over a long period, and the effects may not be apparent for years. Severity of effects. Acute toxicity. The effects are often severe and can result in death or permanent injury in a short time. Chronic toxicity. The effects are often cumulative and may cause long-term health issues, such as cancer, organ damage, or reproductive disorders. Dose-response relationship. Acute toxicity. The severity of the effects is directly related to the dose and concentration of the toxic substance. Chronic toxicity. The cumulative effect of low doses over time leads to health issues, often at lower levels than required for acute toxicity. Examples. Acute toxicity. Carbon monoxide poisoning, cyanide poisoning. Chronic toxicity. Lead poisoning, exposure to asbestos leading to lung cancer. Previous year question UGC NET 2021. Q. Which of the following substances is most likely to cause chronic toxicity through long-term exposure? A. Benzene, which is a known carcinogen, causes chronic toxicity through long-term exposure. UGC NET 2021. Environmental and health implications. Both acute and chronic toxicity have profound implications for environmental health and regulatory policies. In an environmental context, the acute toxicity of pollutants such as pesticides, heavy metals, and industrial chemicals can cause immediate harm to aquatic organisms, wildlife, and human populations, especially in the case of industrial accidents, chemical spills, or high concentration exposure events. On the other hand, chronic toxicity poses a more insidious threat, as pollutants like heavy metals, persistent organic pollutants, POPs, and endocrine disruptors accumulate in the environment and organisms over time, leading to long-term ecosystem degradation and health problems. Strategies for addressing acute and chronic toxicity. Risk assessment and regulation. Toxicologists and environmental scientists assess the risks associated with both acute and chronic toxicity through laboratory testing, environmental monitoring, and epidemiological studies. Regulatory agencies, such as the EPA, Environmental Protection Agency, set safety standards for the permissible levels of toxic substances in air, water, and food. Public awareness and prevention, public health campaigns, regulatory policies, and workplace safety guidelines aim to reduce exposure to toxic substances, particularly in occupational settings or communities near industrial sites. Environmental remediation. For chronic toxicity caused by persistent pollutants, environmental remediation strategies, such as the cleanup of contaminated soils, water treatment, and air purification, are essential in mitigating long-term environmental impacts. Conclusion. Understanding the concepts of acute and chronic toxicity is crucial for assessing the environmental and health risks posed by chemical pollutants. Acute toxicity involves severe, immediate health effects following short-term exposure, while chronic toxicity results from long-term exposure, causing gradual damage that may not manifest for years. Both types of toxicity require careful monitoring and regulation to protect public health and the environment from harmful substances. As toxicologists continue to study the mechanisms and impacts of these toxic agents, preventive measures and risk assessment strategies will remain vital in minimizing exposure and mitigating the harmful effects of toxic substances. Summary of key points. Acute toxicity, short-term, immediate harmful effects, rapid onset, lethal dose LD50 used to assess toxicity. Chronic toxicity, long-term exposure, gradual onset of symptoms, cumulative effects, often leading to chronic diseases like cancer and organ damage. Key examples: acute toxicity, cyanide, carbon monoxide, chronic toxicity, asbestos, benzene. This lecture covers essential concepts that are crucial for understanding how toxic substances affect living organisms in both immediate and long-term contexts. Understanding the difference between acute and chronic toxicity is vital for preparing for the UGC NET JRF environmental science exam, as these concepts frequently appear in the exam. You said, concept of bioassay ChatGPT said. Concept of bioassay, definition, types, and applications in environmental science, UGC NET JRF environmental science, high-level lecture with maximum word limit, paragraph format, based on previous year questions in key areas. A bioassay is a scientific procedure used to assess the potency, effectiveness, and toxicity of a substance such as a chemical, drug, or environmental pollutant by observing its effects on living organisms. The term bioassay refers to any biological test that measures the concentration or activity of a substance, typically through its effects on biological systems or organisms. Bioassays are essential tools in various fields, including environmental monitoring, toxicology, pharmacology, and ecotoxicology, as they provide valuable insights into the potential impact of substances on ecosystems, human health, and wildlife. Definition of bioassay. A bioassay can be defined as a method used to determine the concentration or potency of a substance by measuring its biological effect on a living organism. The effect may involve physical, biochemical, or behavioral changes in the organism, and the results can be quantified to compare the activity of different substances or concentrations. The concept of bioassay is based on the principle that living organisms, or biological systems, respond to the presence of certain substances, and these responses can be measured to infer the characteristics of the substance. Types of bioassay. Bioassays can be broadly categorized into different types based on their application, the organism or biological system used, and the nature of the substance being tested. Some of the common types of bioassays are: acute bioassay. Acute bioassays measure the immediate toxic or harmful effects of a substance following short-term exposure. These assays are used to determine the lethal dose LD50 or the lethal concentration LC50 of a substance, which is the dose or concentration that causes death in 50% of the test organisms. Example: a fish bioassay where a certain concentration of a pesticide is introduced to a tank of fish, and their survival rate is monitored to determine the LC50 of the pesticide. Chronic bioassay. Chronic bioassays assess the long-term effects of a substance on an organism or population over an extended period. These bioassays are used to evaluate the cumulative, sublethal effects of substances that may not cause immediate harm but could result in long-term damage, such as cancer, reproductive issues, or neurological damage. Example: chronic exposure to low concentrations of a heavy metal, such as lead, to study its impact on the growth and reproduction of aquatic organisms. In vivo bioassay. In vivo bioassays involve testing substances on whole, living organisms such as plants, animals, or humans. These tests provide more accurate, real-world data on how a substance affects a biological system, as they take into account complex interactions within the organism. Example: testing the toxicity of a chemical compound on rats or mice by observing physiological changes or behavioral alterations. In vitro bioassay. In vitro bioassays are conducted using isolated cells or tissues rather than whole organisms. These assays are useful for studying the cellular or molecular mechanisms of toxicity and are often used in early-stage testing of chemicals and pharmaceuticals. Example: using cultured human cells to test the cytotoxicity of a new drug or to measure the effect of a chemical on cell growth and division. Immunoassays. Immunoassays are a specific type of bioassay that involves the use of antibodies to detect the presence and concentration of specific substances, such as pathogens, toxins, or pollutants. These assays are often used in environmental monitoring and diagnostic testing. Example: using an enzyme-linked immunosorbent assay, ELISA, to detect the presence of a particular toxin or pathogen in water samples. Applications of bioassay. Bioassays play a crucial role in various fields, including environmental science, toxicology, and pharmacology, where they are used for monitoring pollutants, assessing drug efficacy, and evaluating the safety of chemicals. Some of the major applications of bioassays are: environmental monitoring. Bioassays are widely used to assess the toxicity of pollutants in the environment, including water, soil, and air. By exposing organisms to these pollutants and measuring their responses, bioassays help determine the ecological impact of contaminants and the safety of natural habitats. Example: aquatic bioassays using fish or invertebrates are commonly used to assess the toxicity of chemicals in water bodies, such as pesticides, heavy metals, and industrial effluents. Ecotoxicology. Bioassays are a key tool in ecotoxicology, the study of the effects of toxic substances on ecosystems. They are used to evaluate the potential impact of chemical pollutants on biodiversity, species interactions, and ecosystem functioning. Example: using bioassays to assess the impact of a pesticide on non-target species, such as pollinators, or to study the effects of herbicides on aquatic plant species. In pharmacology, bioassays are used to test the efficacy and safety of new drugs or treatments. In toxicology, bioassays help assess the potential harm of chemicals, pharmaceuticals, and environmental pollutants on human health and wildlife. Example: pharmaceutical companies use bioassays to evaluate the potency of drugs in preclinical trials, while environmental toxicologists use bioassays to study the effects of industrial chemicals on wildlife populations. Regulatory testing. Bioassays are essential for regulatory agencies to assess the safety of new chemicals, agricultural products, and pharmaceuticals before they are approved for commercial use. They help ensure that these products do not pose significant risks to human health or the environment. Example, the U.S. Environmental Protection Agency (EPA) and the Food and Drug Administration (FDA) rely on bioassay data to establish safe exposure limits for chemicals and pesticides. Monitoring of pesticide residues. Bioassays are used to detect pesticide residues in food, water, and soil. These assays help ensure that food products do not exceed the safe levels of pesticide residues, protecting consumers from potential health risks. Example, testing for pesticide residues in agricultural products like fruits and vegetables using bioassays to assess the concentration of specific chemicals. Previous year question, UGC NET 2020. Q. Which of the following is the primary purpose of conducting a bioassay in environmental science? The primary purpose of conducting a bioassay is to assess the toxicity and potency of substances and evaluate their effects on living organisms in the environment. UGC NET 2020. Advantages and limitations of bioassays. Advantages. Relevance to living systems. Bioassays provide real-world data on the effects of substances, as they directly measure the responses of living organisms. Versatility. Bioassays can be used to test a wide range of substances, including chemicals, pharmaceuticals, pollutants, and toxins. Early detection. Bioassays can identify harmful substances and potential risks at an early stage, allowing for the implementation of safety measures before widespread exposure. Limitations. Ethical concerns. In vivo bioassays that involve animal testing can raise ethical concerns related to animal welfare. Species-specific results. The results of bioassays conducted on specific organisms may not always be applicable to other species or ecosystems. Cost and time. Some bioassays, particularly in vivo assays, can be expensive and time-consuming due to the need for large test populations and prolonged observation periods. Conclusion. Bioassays are indispensable tools in environmental science, toxicology, and pharmacology for evaluating the toxicity, potency, and safety of substances. By measuring the biological effects of substances on living organisms, bioassays help scientists, regulators, and policymakers assess potential risks to human health, wildlife, and ecosystems. Whether conducted in the lab using isolated cells or in the field with whole organisms, bioassays provide valuable insights that guide environmental protection efforts, regulatory decisions, and the development of safer chemicals and drugs. Summary of key points. Bioassay definition. A biological test used to assess the concentration or potency of a substance based on its effects on living organisms. Types of bioassays: acute, chronic, in vivo, in vitro, and immunoassays. Applications: environmental monitoring, ecotoxicology, pharmacology, toxicology, and regulatory testing. This detailed lecture will help solidify the concept of bioassays, their types, applications, and significance, providing a comprehensive foundation for your UGC NET JRF environmental science exam preparation. You said, threshold limit value. ChatGPT said. Threshold limit value TLV definition, types, and applications in environmental science. UGC NET JRF environmental science. High level lecture with maximum word limit. Paragraph format based on previous year questions and key areas. The threshold limit value TLV is a term used to describe the concentration of a substance in air, usually expressed as parts per million or micrograms per cubic meter, that is believed to be safe for the general population to be exposed to over a specified period without causing harmful effects. TLVs are primarily used to assess the potential health risks associated with exposure to airborne contaminants, such as chemicals, pollutants, and other hazardous substances in the workplace or environment. These values provide a guideline for limiting exposure and are used by various regulatory bodies, industries, and health organizations to ensure safe working conditions and environmental quality. Definition of threshold limit value TLV. The threshold limit value represents the concentration of a chemical or substance in the air that a worker can be exposed to over the course of an 8-hour workday and a 40-hour workweek without experiencing any adverse health effects. TLVs are set based on scientific research and observations about the potential toxic effects of a substance on human health, with the aim of minimizing the risk of chronic illness, acute toxicity, or other harmful health consequences from exposure. TLVs are typically set by organizations such as the American Conference of Governmental and Industrial Hygienists (ACGIH), which establishes these values as guidelines for acceptable levels of exposure. It is important to note that TLVs are not absolute safety standards but are meant to provide a practical benchmark for managing exposure to hazardous substances. Types of threshold limit values. There are several different types of TLVs, each designed for specific exposure scenarios, including TLV-TWA threshold limit value, time weighted average. The TLV-TWA is the most commonly used type of TLV and refers to the average concentration of a substance in air over an 8-hour workday, typically 40 hours per week. It represents the maximum allowable concentration of a substance that a worker can be exposed to continuously over the course of the workday without significant The threshold limit value TLV is a term used to describe the concentration of a substance in air, usually expressed as parts per million or micrograms per cubic meter, that is believed to be safe for the general population to be exposed to over a specified period without causing harmful effects. TLVs are primarily used to assess the potential health risks associated with exposure to airborne contaminants, such as chemicals, pollutants, and other hazardous substances in the workplace or environment. The threshold limit value TLV is a term used to describe the concentration of a substance in air, usually expressed as parts per million or micrograms per cubic meter, that is believed to be safe for the general population to be exposed to over a specified period without causing harmful effects. TLVs are primarily used to assess the potential health risks associated with exposure to airborne contaminants, such as chemicals, pollutants, and other hazardous substances in the workplace or environment. These values provide a guideline for limiting exposure and are used by various regulatory bodies, industries, and health organizations to ensure safe working conditions and environmental quality. Definition of threshold limit value TLV. The threshold limit value represents the concentration of a chemical or substance in the air that a worker can be exposed to over the course of an 8-hour workday and a 40-hour workweek without experiencing any adverse health effects. TLVs are set based on scientific research and observations about the potential toxic effects of a substance on human health, with the aim of minimizing the risk of chronic illness, acute toxicity, or other harmful health consequences from exposure. TLVs are typically set by organizations such as the American Conference of Governmental and Industrial Hygienists (ACGIH), which establishes these values as guidelines for acceptable levels of exposure. It is important to note that TLVs are not absolute safety standards but are meant to provide a practical benchmark for managing exposure to hazardous substances. Types of threshold limit values. There are several different types of TLVs, each designed for specific exposure scenarios, including TLV-TWA threshold limit value, time weighted average. The TLV-TWA is the most commonly used type of TLV and refers to the average concentration of a substance in air over an 8-hour workday, typically 40 hours per week. It represents the maximum allowable concentration of a substance that a worker can be exposed to continuously over the course of the workday without significant health risks. Example, the TLV-TWA for carbon monoxide CO is 25 ppm, meaning that over an 8-hour workday, exposure to this level of CO is considered safe for workers. TLV-STDL threshold limit value, short-term exposure limit. The TLV-STEL is the maximum allowable concentration of a substance to which a worker can be exposed for a short period, typically 15 minutes during the workday. It is used for substances that may cause immediate harmful effects if exposure is too high in a short time. Example, the TLV-STEL for hydrogen sulfide H2S is 15 ppm, meaning that short-term exposure to this level for a duration of 15 minutes is acceptable, but longer exposure to higher concentrations could lead to health issues. TLVC TLVC threshold limit value, ceiling limit. The TLVC represents the maximum concentration of a substance that should never be exceeded at any time, even for a short period. It is used for chemicals that have an immediate toxic effect at high concentrations, regardless of TLVC threshold limit value, ceiling limit. The TLVC represents the maximum concentration of a substance that should never be exceeded at any time, even for a short period. It is used for chemicals that have an immediate toxic effect at high concentrations, regardless of how long the exposure lasts. Example, the TLVC for ammonia NH3 is 35 ppm, meaning that the concentration of ammonia in the air should never exceed this level at any time. TLVRES threshold limit value, respiratory protection. The TLVRES is a specific value used when workers must rely on respiratory protection due to the high toxicity of a substance. This value is used to ensure that the concentration of a toxic substance does not exceed a level where protection is no longer effective. Example, in cases where respiratory protection is required, the TLVRES ensures that even with protection, the exposure remains below hazardous levels. Applications of threshold limit value TLV. The concept of TLVs plays a critical role in several important areas related to public health, workplace safety, and environmental protection. Below are the key applications of TLVs. Occupational health and safety. TLVs are widely used in industrial settings to regulate the exposure of workers to hazardous substances. By establishing safe exposure limits, TLVs help to prevent occupational diseases, accidents, and injuries caused by toxic substances in the workplace. Example, workers in factories dealing with chemicals like asbestos or benzene must adhere to the TLVTWA guidelines to minimize the risk of lung diseases, cancers, and other health problems associated with prolonged exposure. Environmental monitoring. TLVs are also applied in environmental monitoring to ensure that air quality in public spaces, communities, and natural environments remains at safe levels. Regulatory agencies use TLVs to establish guidelines for acceptable levels of pollutants in ambient air, thus preventing harmful exposure to the public. Example, governments and environmental agencies use TLVs to set standards for pollutants such as carbon monoxide, CO, sulfur dioxide, SO2, and nitrogen dioxide number 2 in urban air, thereby protecting the health of the general population. Setting regulatory standards. TLVs are frequently used as a basis for developing regulations and standards for hazardous chemicals in the workplace and the environment. Agencies like the Occupational Safety and Health Administration (OSHA) in the U.S. use TLVs to enforce workplace safety laws. Example, the TLVTWA for a substance like arsenic might influence the Occupational Safety and Health Administration (OSHA) to regulate its concentration in the workplace environment to protect workers from exposure. Health risk assessment. TLVs are useful tools for conducting health risk assessments of environmental pollutants. Environmental health scientists use TLVs to evaluate the risk posed by various contaminants and to establish guidelines for mitigating exposure risks. Example, a study of radon exposure might use TLV guidelines to assess safe levels of radon concentration in indoor environments, such as homes and offices, where long-term exposure could lead to cancer. Emergency response. TLVs can also aid in emergency response situations where exposure to hazardous chemicals has occurred. By using the TLV values, responders can determine the appropriate actions to limit exposure and ensure worker safety. Example, in the event of a chemical spill or leak, such as chlorine gas, emergency response teams can use TLVC values to assess the danger and evacuate affected areas if the concentration exceeds safe limits. Previous year question, UGC NET 2021. Q. What is the purpose of the threshold limit value TLV in occupational health? The threshold limit value TLV is used to limit exposure to hazardous substances in the workplace and ensure worker safety. It is defined as the concentration of a substance in the air that workers can be exposed to over an 8-hour workday without experiencing adverse health effects. UGC NET 2021. Advantages and limitations of TLV's advantages. Health protection. TLVs help to protect workers and the public from harmful health effects of exposure to chemicals and pollutants. Regulatory framework. TLVs provide a scientific basis for creating and enforcing regulations related to air quality and workplace safety. Preventive measure. TLVs allow for early intervention to prevent long-term health effects and occupational diseases. Limitations. Not absolute standards. TLVs are guidelines, not absolute safety standards, and may not account for all potential health risks, such as individual sensitivities. Variability. TLVs can vary based on factors such as age, health status, and exposure duration, which may make them less effective for vulnerable populations. Lack of specificity. Some TLVs are not substance specific and may not apply well to all exposure scenarios, especially in complex environments. Conclusion. The threshold limit value TLV is a vital concept in both occupational health and environmental science, serving as a guideline to ensure the safety of individuals exposed to harmful substances. It helps regulatory agencies and organizations establish exposure limits to protect workers from acute and chronic health effects. TLVs are widely used in environmental monitoring, risk assessments, and emergency response protocols, making them indispensable tools in the management of public health and safety. Understanding TLVs is crucial for preparing for environmental science exams and ensuring the protection of workers and the general public from hazardous chemical exposures. Summary of key points. TLV definition: a guideline indicating the maximum concentration of a substance in air that is safe for exposure over an 8-hour workday without causing harmful effects. Types of TLVs: TLVTWA, TLV-STEL, TLVC, and TLV-RES. Applications: occupational health, environmental monitoring, regulatory standards, health risk assessment, and emergency response. This detailed lecture provides the essential information on threshold limit values TLV, ensuring a solid foundation for your UGC NET JRF environmental science exam preparation. You said, margin of safety, ChatGPT said. Margin of safety, definition, importance, and applications in toxicology and environmental science UGC NET JRF environmental science, high-level lecture with maximum word limit, paragraph format, based on previous year questions and key areas. The margin of safety MOS is a concept used in toxicology and environmental science to quantify the difference between the no observed adverse effect level NOAEL or lowest observed adverse effect level LOAEL and the estimated exposure level to a substance. It provides a measure of the safety of a substance for humans or the environment, ensuring that exposure to potentially harmful chemicals, pollutants, or toxicants remains well below levels that could cause adverse health effects. The margin of safety is particularly important in risk assessments, as it helps determine the safe limits for exposure to hazardous substances. Definition of margin of safety MOS. The margin of safety is essentially the ratio between the no effect level NOEL or NOAEL and the expected exposure level of a substance. It is expressed mathematically as MOS equals NOAEL EXPOSURE. LEVEL MOS equals exposure level NOEL, where NOAEL refers to the highest dose of a substance that does not produce any observed adverse effect in a population. Exposure level is the amount of the substance that individuals are exposed to in a given environment, which could be based on workplace exposure or environmental levels of pollutants. A larger margin of safety indicates a greater level of protection, meaning the exposure to a substance is far below the threshold where adverse effects may occur. A smaller margin of safety suggests that the substances being used are exposed at levels closer to those that could cause harm, thus presenting a higher risk. Importance of margin of safety in toxicology and environmental science. The concept of the margin of safety is critical in toxicology because it helps regulators, industries, and environmental agencies determine the safe levels of exposure to chemicals, particularly for substances that can have long-term health effects such as carcinogens, neurotoxins, or endocrine disruptors. The margin of safety is used to ensure that public health is not jeopardized by unsafe exposure to hazardous substances. Risk assessment. The margin of safety is a key factor in risk assessment, where it is used to evaluate the potential health risks posed by exposure to chemicals and pollutants. A wide margin of safety indicates a low risk, whereas a narrow margin of safety may necessitate stricter controls and regulations. Regulatory guidelines. Regulatory bodies like the Environmental Protection Agency (EPA) and the World Health Organization (WHO) use the margin of safety to set guidelines for maximum allowable exposure levels in various environments, e.g., workplace, residential areas, or natural ecosystems. The margin of safety provides a buffer between known safe levels and potential real-world exposure, ensuring protection for sensitive populations, such as children, pregnant women, and the elderly. Public health protection. The margin of safety is crucial for protecting public health, as it accounts for potential uncertainties in scientific data, individual variability, and environmental factors that may influence the effects of exposure. A wider margin of safety reduces the likelihood of unexpected harmful effects on human or environmental health. Applications of margin of safety in various fields. Pharmaceuticals and drug development. In pharmacology, the margin of safety is used to determine safe dosage ranges for drugs. The therapeutic index (TI), a similar concept, is the ratio of the dose required for a therapeutic effect to the dose that causes toxicity. A higher therapeutic index or margin of safety means that the drug has a wider safe dosage range, making it safer for use. Example: a drug with a therapeutic dose of 10 mg and a toxic dose of 100 mg would have a high margin of safety, as there is a large difference between the effective and toxic doses. Environmental toxicology. In environmental toxicology, the margin of safety is used to assess the risks associated with pesticides, heavy metals, and other pollutants. Regulatory agencies use this concept to set maximum allowable concentrations of harmful substances in drinking water, air, and soil. Example: if a chemical like lead has a NOAEL of 10 micrograms per cubic meter in air and the expected exposure level in a community is 0.1 micrograms per cubic meter, the margin of safety is 100. This indicates that the exposure is far below levels that could cause harm, providing a significant safety margin. Food safety and additives. The margin of safety is also applied in the food industry to determine the safety of food additives, preservatives, and contaminants. The margin of safety ensures that even when people consume foods containing these substances, they are not exposed to dangerous levels. Example: the acceptable daily intake (ADI) for a food additive like aspartame is based on its NOAEL in animal studies, and a wide margin of safety is used to ensure that the levels of the additive in food products are far below those that could cause adverse health effects. Environmental policy and pollution control. Governments and environmental agencies use the margin of safety to set air and water quality standards. By applying a wide margin of safety to exposure levels of pollutants, they ensure that even vulnerable groups are not exposed to harmful levels of contaminants. Example: the National Ambient Air Quality Standards (NAAQS) for pollutants such as ozone O3 and particulate matter PM2.5 are set with a margin of safety to protect public health, especially in high-risk groups like children and individuals with respiratory conditions. Previous year question: UGC NET 2019 Q. Why is the margin of safety important in environmental risk assessment? The margin of safety is critical in environmental risk assessment because it ensures that exposure to hazardous substances is well below levels that could cause adverse health effects. It provides a buffer between safe exposure levels and potential harmful concentrations, thus protecting human and environmental health from toxic substances. UGC NET 2019. Advantages and limitations of margin of safety. Advantages. Protective measure. The margin of safety helps to protect sensitive individuals and vulnerable populations by setting exposure limits far below levels that could cause harm. Conservative approach. It takes into account uncertainties and variability in data, offering a conservative approach to setting safety standards. Public confidence. By using a wide margin of safety, regulatory bodies can increase public confidence in the safety of chemicals, pollutants, and drugs. Limitations. Overestimation. A wide margin of safety may lead to unnecessary regulations or restrictions, potentially leading to economic losses or overprotection. Data uncertainties. The margin of safety relies on the accuracy of data such as NOAEL, which may be difficult to determine in certain cases. Incomplete or uncertain data can affect the reliability of the safety margin. May not account for long-term effects. The margin of safety may not fully account for cumulative or long-term effects of exposure, which can pose risks even if short-term exposure remains within safe limits. Conclusion. The margin of safety (MOS) is a crucial concept in toxicology, environmental science, and public health protection. It provides a quantitative measure of the safety buffer between known safe exposure levels and the potential risk to health, ensuring that substances, whether chemicals, pollutants, or drugs, are used in ways that minimize the risk of harm. By considering uncertainties, variability, and long-term effects, the margin of safety serves as an essential tool for regulatory agencies, industries, and policymakers in establishing safe exposure limits that protect human health and the environment. Summary of key points. Margin of safety (MOS) quantifies the difference between safe exposure levels and actual exposure to chemicals or pollutants. Mathematical formula: MOS equals NOAEL exposure level. Applications: used in pharmaceutical development, environmental toxicology, food safety, and pollution control to ensure safety. Advantages: provides a protective buffer and takes uncertainties into account. Limitations: may lead to overregulation and does not always account for long-term effects. This lecture provides a thorough understanding of margin of safety (MOS), an essential concept for your preparation in UGC NET JRF Environmental Science. You said. Therapeutic index. ChatGPT said. Therapeutic index. Definition, importance, and applications in toxicology and pharmacology. UGC NET JRF Environmental Science. High-level lecture with maximum word limit. Paragraph format based on previous year questions in key areas. The therapeutic index (TI) is a fundamental concept in pharmacology and toxicology used to assess the safety and efficacy of a drug or chemical. It represents the ratio between the toxic dose and the therapeutic dose of a substance. Essentially, it quantifies the margin of safety of a drug, providing insight into how much a drug can be administered before it starts to produce harmful or toxic effects. The therapeutic index is crucial for determining safe dosage levels for drugs, particularly those with narrow therapeutic windows, where the difference between the effective dose and the harmful dose is small. Definition of therapeutic index (TI). The therapeutic index is defined as the ratio of the dose of a drug that causes toxic effects (TD50 or LD50) to the dose that produces the desired therapeutic effect (ED50). It is calculated as TI equals LD50 or TD50E. D50 TI equals ED50. LD50 or TD50. Where LD50 refers to the lethal dose that kills 50% of the population. TD50 refers to the toxic dose that causes toxic effects in 50% of the population. ED50 refers to the effective dose that achieves the desired therapeutic effect in 50% of the population. LD50 refers to the lethal dose that kills 50% of the population. TD50 refers to the toxic dose that causes toxic effects in 50% of the population. ED50 refers to the effective dose that achieves the desired therapeutic effect in 50% of the population. A higher TI indicates a greater safety margin, meaning there is a large difference between the effective dose and the toxic dose. In contrast, a lower TI suggests that there is a smaller safety margin, and the drug or substance is more likely to cause adverse effects at doses that are effective in treating the target condition. Importance of therapeutic index. The therapeutic index is vital for ensuring drug safety, particularly when developing and administering pharmaceuticals. The TI helps healthcare professionals, pharmaceutical companies, and regulatory bodies understand the potential risks and benefits of a drug. Here are some of the key reasons why the TI is important. Safety assessment. The TI helps to assess the safety profile of a drug. A high TI means the drug is relatively safe since the dose that produces beneficial effects is much lower than the dose that causes harm. Conversely, a low TI indicates a narrow safety margin, requiring more careful dosing and monitoring. Dosing guidelines. The therapeutic index is instrumental in determining the appropriate dosing for a drug. Drugs with a narrow therapeutic index must be prescribed with caution, and frequent monitoring is necessary to avoid reaching toxic levels. Regulatory standards. Regulatory agencies, such as the FDA and EMA, use the therapeutic index to evaluate whether a drug should be approved for use. Drugs with a narrow therapeutic index often face stricter regulation and may require more extensive clinical trials to ensure their safety. Pharmacovigilance. In the post-marketing phase, the TI helps monitor adverse drug reactions. Drugs with low therapeutic indices are more likely to cause serious side effects, and thus, ongoing surveillance is crucial to detect issues early. Comparative safety. The TI allows the comparison of the safety of different drugs used to treat the same condition. Drugs with a higher TI are typically preferred over those with a lower TI, as they are less likely to cause unwanted toxic effects. Applications of therapeutic index in pharmacology. The concept of the therapeutic index is applied across various domains in pharmacology and toxicology. Drug development and testing. In the early stages of drug development, the therapeutic index is used to compare the potential safety and efficacy of different candidates. Drugs with a wide TI are more likely to be advanced to clinical trials, as they present fewer risks to patients. If a drug is found to have a low TI, it may either be modified or dropped from further testing. Cancer treatment. Many chemotherapeutic agents used in cancer treatment have a narrow therapeutic index, meaning that they have a small margin between the dose that is effective and the dose that is toxic. Chemotherapy drugs are often toxic to both cancerous and normal cells, so careful dosing and monitoring are required. The therapeutic index helps doctors balance the need for efficacy with the risk of toxicity, ensuring that the patient receives an optimal dose without crossing into the toxic range. Cardiovascular drugs. Certain cardiovascular drugs, such as digoxin, have a low therapeutic index. Digoxin is used to treat heart failure and arrhythmias but can cause toxicity at doses near the therapeutic level. The therapeutic index helps clinicians adjust doses to avoid toxic effects, particularly in patients with kidney dysfunction who may have altered drug metabolism. Toxicology and environmental exposure. In environmental toxicology, the therapeutic index can be applied to assess the safety of chemicals, pollutants, and environmental contaminants. A substance with a low TI is more likely to cause adverse effects at low exposure levels, necessitating stringent regulations and safety measures. Veterinary medicine. In veterinary medicine, the therapeutic index helps in determining the safe dosages for animals, ensuring that the administered dose is adequate to treat diseases without causing toxicity. Given that animals can have different pharmacokinetics compared to humans, the TI is an essential tool in veterinary drug formulation and administration. Factors affecting therapeutic index. Several factors can influence the therapeutic index of a drug or substance. These include age and health status of the patient. Elderly individuals, children, and people with certain health conditions, e.g., liver or kidney disease, may metabolize drugs differently, affecting the TI. For instance, reduced liver function can lead to higher drug concentrations in the blood, increasing the risk of toxicity. Drug interactions. The co-administration of other drugs can affect the absorption, distribution, metabolism, or excretion of a drug, thereby altering its therapeutic index. Drug interactions can increase toxicity or reduce the drug's effectiveness. Genetic variations. Genetic differences can impact how individuals respond to drugs. Certain populations may have genetic mutations that lead to altered drug metabolism, influencing the therapeutic index of certain drugs. Route of administration. The method of drug delivery, oral, intravenous, etc., can affect how the drug is absorbed, distributed, and metabolized, influencing the therapeutic index. Some routes may lead to faster drug absorption, which can increase the risk of reaching toxic levels. Previous year question UGC-NET 2018 Q. What does a low therapeutic index of a drug indicate? A low therapeutic index indicates that there is a small margin between the dose required for therapeutic effect and the dose that causes toxicity. Drugs with a narrow therapeutic index are more prone to cause adverse effects at doses near the therapeutic range and thus require careful monitoring and precise dosing. UGC-NET 2018. Advantages and limitations of therapeutic index advantages. Simplifies safety evaluation. The therapeutic index simplifies the safety evaluation of drugs, providing a quick and clear measure of a drug's safety margin. Helps guide dosing. It helps healthcare professionals determine appropriate dosages and monitor patients to avoid toxic effects. Useful in drug comparisons. The TI allows for the comparison of the relative safety of different drugs used to treat similar conditions. Limitations. Does not account for long-term effects. The therapeutic index focuses on acute toxicity and effectiveness but may not fully account for long-term adverse effects or cumulative toxicity over time. May overlook individual variability. It is based on population averages, and the TI may not adequately reflect variability in drug metabolism between individuals, particularly in vulnerable groups, e.g., children, elderly, or patients with chronic diseases. Narrow TI drugs require special consideration. Drugs with a narrow therapeutic index require meticulous monitoring and can be difficult to manage, especially in patients with variable drug absorption or metabolism. Conclusion. The therapeutic index TI is an essential tool in pharmacology and toxicology, offering a quantitative assessment of the safety margin of a drug or substance. It plays a vital role in determining safe dosages, ensuring effective treatment, and minimizing toxicity risks. Understanding and applying the therapeutic index is critical for clinicians, regulatory agencies, and pharmaceutical developers to ensure the safety of drugs and chemicals for human health and the environment. Summary of key points. Therapeutic index TI quantifies the safety margin between the effective dose ED50 and the toxic dose TD50 or LD50. High TI indicates a safer drug with a wider margin between therapeutic and toxic doses. Low TI drugs require careful monitoring due to their higher risk of toxicity. The TI is applied in drug development, cancer treatment, cardiovascular medicine, and environmental toxicology. Limitations include its inability to account for long-term effects and individual variability. This lecture provides an in-depth understanding of the therapeutic index TI, crucial for your preparation in UGC-NET JRF Environmental Science. You said, biotransformation. ChatGPT said. Biotransformation, definition, mechanisms, importance, and applications in environmental science. UGC-NET JRF Environmental Science, high-level lecture with maximum word limit, paragraph format, based on previous year questions and key areas. Biotransformation refers to the process by which living organisms, especially microorganisms, plants, and animals, modify the chemical structure of a substance, typically a toxic or xenobiotic compound, into a more water-soluble form. This modification is primarily aimed at facilitating the excretion of the substance from the body. Biotransformation can convert a substance into a less toxic or more toxic form, and it plays a vital role in detoxifying pollutants, pharmaceuticals, and other foreign chemicals. Definition of biotransformation. Biotransformation is a chemical alteration of a compound through enzymatic reactions that usually make the compound more hydrophilic, water-soluble, and, therefore, easier to excrete. These alterations can involve processes such as oxidation, reduction, hydrolysis, and conjugation. This process is primarily carried out by various enzymes, including those found in the liver, but it can also occur in other tissues, such as the lungs, kidneys, and gut, depending on the organism and the type of compound involved. Phases of biotransformation. Biotransformation occurs in two main phases. Phase 1 reactions, functionalization reactions. In phase 1, enzymes such as cytochrome P450, CYP450 enzymes, flavin-containing monooxygenases, and oxidases introduce or expose functional groups such as hydroxyl O-amino NH2 carboxyl COOH and sulfhydryl CH groups on the xenobiotic compound. This modification often makes the compound more polar, but it may not always result in complete detoxification. Oxidation, reduction, and hydrolysis are common reactions in this phase. For example, the oxidation of a drug like acetaminophen paracetamol by cytochrome P450 results in the formation of a metabolite that can then undergo further transformation in phase 2. Phase 2 reactions, conjugation reactions. In phase 2, the metabolite from phase 1 undergoes conjugation with endogenous molecules such as glucuronic acid, sulfate, glutathione, or amino acids to form highly water-soluble conjugates. This conjugation typically results in a more hydrophilic product, which is easier to excrete from the body through urine or bile. Glucuronidation, sulfation, acetylation, and glutathione conjugation are common conjugation reactions. For example, in the case of acetaminophen, the initial product from phase 1 can be conjugated with glucuronic acid to form a glucuronide conjugate, which is then excreted in the urine. Importance of biotransformation. Biotransformation plays several essential roles in living organisms and the environment. Detoxification. One of the primary roles of biotransformation is the detoxification of xenobiotics, foreign compounds, including drugs, pesticides, industrial chemicals, and pollutants. This process makes potentially harmful substances more easily excreted and thus less likely to accumulate in tissues, thereby protecting the organism from toxicity. Environmental cleanup. Biotransformation is a key process in bioremediation, where microorganisms or plants are used to detoxify or degrade pollutants in the environment. Many soil bacteria and fungi are capable of biotransforming toxic compounds like pesticides, heavy metals, and organic solvents, rendering them less harmful to the ecosystem. Phytoremediation using plants to clean up contaminated soils also relies on biotransformation, where plants metabolize and neutralize harmful chemicals in the soil. Biotransformation refers to the process by which living organisms, especially microorganisms, plants, and animals, modify the chemical structure of a substance, typically a toxic or xenobiotic compound, into a more water-soluble form. This modification is primarily aimed at facilitating the excretion of the substance from the body. Biotransformation can convert a substance into a less toxic or more toxic form, and it plays a vital role in detoxifying pollutants, pharmaceuticals, and other foreign chemicals. Definition of biotransformation. Biotransformation is the chemical alteration of a compound through enzymatic reactions that usually make the compound more hydrophilic, water-soluble, and, therefore, easier to excrete. These alterations can involve processes such as oxidation, reduction, hydrolysis, and conjugation. This process is primarily carried out by various enzymes, including those found in the liver, but it can also occur in other tissues, such as the lungs, kidneys, and gut, depending on the organism and the type of compound involved. Phases of biotransformation. Biotransformation occurs in two main phases. Phase 1 reactions, functionalization reactions. In phase 1, enzymes such as cytochrome P450, CYP450 enzymes, flavin-containing monooxygenases, and oxidases introduce or expose functional groups such as hydroxyl O-amino NH2 carboxyl COOH and sulfhydryl CH groups on the xenobiotic compound. This modification often makes the compound more polar, but it may not always result in complete detoxification. Oxidation, reduction, and hydrolysis are common reactions in this phase. For example, the oxidation of a drug like acetaminophen paracetamol by cytochrome P450 results in the formation of a metabolite that can then undergo further transformation in phase 2. Phase 2 reactions, conjugation reactions. In phase 2, the metabolite from phase 1 undergoes conjugation with endogenous molecules such as glucuronic acid, sulfate, glutathione, or amino acids to form highly water-soluble conjugates. This conjugation typically results in a more hydrophilic product, which is easier to excrete from the body through urine or bile. Glucuronidation, sulfation, acetylation, and glutathione conjugation are common conjugation reactions. For example, in the case of acetaminophen, the initial product from phase 1 can be conjugated with glucuronic acid to form a glucuronide conjugate, which is then excreted in the urine. Importance of biotransformation. Biotransformation plays several essential roles in living organisms and the environment. Detoxification. One of the primary roles of biotransformation is the detoxification of xenobiotics, foreign compounds, including drugs, pesticides, industrial chemicals, and pollutants. This process makes potentially harmful substances more easily excreted and thus less likely to accumulate in tissues, thereby protecting the organism from toxicity. Environmental cleanup. Biotransformation is a key process in bioremediation, where microorganisms or plants are used to detoxify or degrade pollutants in the environment. Many soil bacteria and fungi are capable of biotransforming toxic compounds like pesticides, heavy metals, and organic solvents, rendering them less harmful to the ecosystem. Phytoremediation using plants to clean up contaminated soils also relies on biotransformation, where plants metabolize and neutralize harmful chemicals in the soil. Pharmacokinetics. In drug metabolism, biotransformation determines the pharmacokinetics of a drug, including its absorption, distribution, metabolism, and excretion ADME. The rate and extent of biotransformation affect the drug's efficacy, toxicity, and half-life in the body. Prodrugs, which are inactive compounds that become active after biotransformation, are designed to optimize drug delivery and minimize side effects. Toxicity and toxicokinetics. Biotransformation can also lead to the formation of toxic metabolites that may cause adverse effects. For instance, acetaminophen paracetamol is generally safe at therapeutic doses but can form a toxic metabolite in the liver when taken in excess, leading to liver damage. This underscores the importance of understanding the biotransformation pathways of drugs and chemicals. Metabolic resistance in pathogens and pests. Biotransformation processes are also exploited by pests, pathogens, and other organisms to develop resistance to chemicals like pesticides or antibiotics. Through biotransformation, these organisms can metabolize and inactivate the chemicals, rendering them ineffective. Factors influencing biotransformation. Several factors can affect the efficiency and outcome of biotransformation reactions. Enzyme activity. The activity of metabolizing enzymes such as cytochrome P450 enzymes varies among individuals and species. Factors such as genetics, age, diet, and health status can influence enzyme levels and activities, impacting the rate and extent of biotransformation. For example, individuals with genetic polymorphisms may have different rates of drug metabolism, which can influence drug efficacy and toxicity. Environmental conditions. Environmental factors such as temperature, pH, and oxygen levels can influence the biotransformation rates of chemicals, particularly in microorganisms used in bioremediation processes. Cofactors and company substrates. The availability of cofactors such as NADPH, ATP, and glutathione is crucial for the biotransformation processes. These molecules help enzymes in the metabolic conversion of compounds. Interaction with other chemicals. The presence of other substances, including drugs and toxins, can affect biotransformation. Certain drugs can inhibit or induce the activity of cytochrome P450 enzymes, altering the metabolism of other drugs or chemicals. Applications of biotransformation pharmacology. Biotransformation is central to understanding drug metabolism, pharmacokinetics, and drug interactions. The study of biotransformation pathways helps in designing drugs with better bioavailability, fewer side effects, and targeted action. Prodrugs are designed to undergo biotransformation into their active forms, improving the therapeutic profile. Bioremediation. Microorganisms capable of biotransforming pollutants such as petroleum hydrocarbons, pesticides, and heavy metals play a crucial role in environmental cleanup. This biotransformation is central to bioremediation strategies, which use natural organisms or engineered microorganisms to degrade pollutants in contaminated environments. Toxicology and environmental protection. Biotransformation is a key process in understanding the toxicity of environmental pollutants and industrial chemicals. The ability to biotransform xenobiotics determines how long pollutants persist in the environment and their potential to cause harm to humans and wildlife. Previous year questions on biotransformation. Q1 UGC NET 2019. What is the role of biotransformation in pharmacology? A1. Biotransformation plays a crucial role in drug metabolism, altering the chemical structure of drugs to enhance their excretion and minimize toxicity. The phase 1 reactions typically involve oxidation and hydrolysis, while phase 2 reactions involve conjugation with endogenous molecules to make the drug water soluble and easily excreted by the body. UGC NET 2019. Q2 UGC NET 2020. Which of the following factors can affect biotransformation rates in organisms? Enzyme activity, environmental temperature, genetic polymorphism. A2. All of the above factors can affect biotransformation rates. Changes in enzyme activity, environmental conditions, and genetic variations can influence the metabolism and detoxification capacity of an organism. UGC NET 2020. Conclusion. Biotransformation is a critical process in pharmacology, toxicology, and environmental science, governing how organisms metabolize and detoxify substances. Its role in detoxification, bioremediation, and drug metabolism underscores its significance across various fields, from environmental cleanup to pharmaceutical development. Understanding biotransformation is essential for improving drug safety, enhancing bioremediation strategies, and mitigating environmental toxicity. This lecture provides a comprehensive understanding of biotransformation, with relevant applications to the UGC NET JRF environmental science exam. You said, major water. Borne diseases and airborne microbes. NO table ChatGPT said. Major waterborne diseases and airborne microbes. Key concepts for UGC NET JRF environmental science. UGC NET JRF environmental science. High-level lecture with maximum word limit. Paragraph format, based on previous year questions and key areas. Waterborne and airborne diseases are significant public health concerns worldwide, especially in regions with limited access to clean water, sanitation, and healthcare infrastructure. These diseases are caused by microorganisms that are transmitted through water and air, respectively. Understanding these diseases and the pathogens involved is crucial for public health management and environmental science. Waterborne diseases. Waterborne diseases are caused by microorganisms that are transmitted through contaminated water sources. These diseases are a major concern in areas where water quality is compromised, such as in developing countries, disaster-stricken areas, and regions with inadequate sewage treatment systems. Pathogens in water can include bacteria, viruses, protozoa, and parasites. The key factors leading to waterborne diseases are poor sanitation, contaminated drinking water, and lack of proper waste disposal. Common waterborne diseases and their pathogens: cholera. Pathogen: Vibrio cholerae bacterium. Transmission: ingestion of water contaminated with feces from an infected person. Symptoms: severe diarrhea, vomiting, dehydration, and electrolyte imbalances. If untreated, cholera can lead to death within hours due to dehydration. Prevention: safe drinking water, proper sanitation, and vaccination. Typhoid fever. Pathogen: Salmonella enterica serotype type E bacterium. Transmission: contaminated food and water, especially through the fecal-oral route. Symptoms: fever, abdominal pain, weakness, and diarrhea or constipation. Prevention: drinking clean water, proper food hygiene, and vaccination. Dysentery. Pathogen: Shigella species bacteria and Entamoeba histolytica protozoa. Transmission: contaminated water or food. Symptoms: bloody diarrhea, abdominal cramps, and dehydration. Prevention: proper sanitation, clean water supply, and hand hygiene. Hepatitis A. Pathogen: hepatitis virus (HAV). Transmission: fecal-oral route through contaminated water. Symptoms: jaundice, fatigue, abdominal pain, nausea, and vomiting. Prevention: vaccination, improved sanitation, and avoiding contaminated food and water. Giardiasis. Pathogen: Giardia lamblia protozoan parasite. Transmission: contaminated drinking water or food. Symptoms: diarrhea, stomach cramps, and bloating. Prevention: safe drinking water, proper filtration, and hygiene practices. Cryptosporidiosis. Pathogen: Cryptosporidium species protozoan parasite. Transmission: contaminated water, especially in swimming pools and drinking water. Symptoms: diarrhea, stomach cramps, and nausea. Prevention: ensuring clean water supplies and proper water treatment. Amoebiasis. Pathogen: Entamoeba histolytica amoeba. Transmission: ingestion of biotransformation is a critical process in pharmacology, toxicology, and environmental science, governing how organisms metabolize and detoxify substances. Its role in detoxification, bioremediation, and drug metabolism underscores its significance across various fields, from environmental cleanup to pharmaceutical development. Understanding biotransformation is essential for improving drug safety, enhancing bioremediation strategies, and mitigating environmental toxicity. This lecture provides a comprehensive understanding of biotransformation, with relevant applications to the UGC NET JRF environmental science exam. You said, major water. Borne diseases and airborne microbes. NO table ChatGPT said. Major waterborne diseases and airborne microbes. Key concepts for UGC NET JRF environmental science. UGC NET JRF environmental science. High-level lecture with maximum word limit. Paragraph format, based on previous year questions and key areas. Waterborne and airborne diseases are significant public health concerns worldwide, especially in regions with limited access to clean water, sanitation, and healthcare infrastructure. These diseases are caused by microorganisms that are transmitted through water and air, respectively. Understanding these diseases and the pathogens involved is crucial for public health management and environmental science. Waterborne diseases. Waterborne diseases are caused by microorganisms that are transmitted through contaminated water sources. These diseases are a major concern in areas where water quality is compromised, such as in developing countries, disaster-stricken areas, and regions with inadequate sewage treatment systems. Pathogens in water can include bacteria, viruses, protozoa, and parasites. The key factors leading to waterborne diseases are poor sanitation, contaminated drinking water, and lack of proper waste disposal. Common waterborne diseases and their pathogens: cholera. Pathogen: Vibrio cholerae bacterium. Transmission: ingestion of water contaminated with feces from an infected person. Symptoms: severe diarrhea, vomiting, dehydration, and electrolyte imbalances. If untreated, cholera can lead to death within hours due to dehydration. Prevention: safe drinking water, proper sanitation, and vaccination. Typhoid fever. Pathogen: Salmonella enterica serotype type E bacterium. Transmission: contaminated food and water, especially through the fecal-oral route. Symptoms: fever, abdominal pain, weakness, and diarrhea or constipation. Prevention: drinking clean water, proper food hygiene, and vaccination. Dysentery. Pathogen: Shigella species bacteria and Entamoeba histolytica protozoa. Transmission: contaminated water or food. Symptoms: bloody diarrhea, abdominal cramps, and dehydration. Prevention: proper sanitation, clean water supply, and hand hygiene. Hepatitis A. Pathogen: hepatitis virus (HAV). Transmission: fecal-oral route through contaminated water. Symptoms: jaundice, fatigue, abdominal pain, nausea, and vomiting. Prevention: vaccination, improved sanitation, and avoiding contaminated food and water. Giardiasis. Pathogen: Giardia lamblia protozoan parasite. Transmission, contaminated drinking water or food. Symptoms, diarrhea, stomach cramps, and bloating. Prevention, safe drinking water, proper filtration, and hygiene practices. Cryptosporidiosis.